Hey guys, this is the second section of stoichiometry notes for today. Our question of the day is how many grams would 2.55 times 10 to the 24th molecules of sodium nitrate weigh? So you should be writing out the equation for sodium nitrate. We know we have that many molecules of it. You can use that mole map. I would be dividing by Avogadro's number to get an answer on this one. Okay, so more about using the mole. Besides doing basic conversions, what use does the mole have? Knowing the percent composition by mass of each element in a compound is very practical and easy to use. So let's look at an example. Farmers use primarily two fertilizers, ammonium nitrate and ammonium phosphate. Which one contains a greater percentage of nitrogen by mass? So we're going to assume we have 1 mole of each compound. Step 1 is to just write out our chemical formula. We need to know what ammonium nitrate and ammonium phosphate look like. So here's ammonium nitrate, and here's ammonium phosphate. We're trying to figure out what percent of each of those compounds is made up of nitrogen. So here's how you do that. Okay. Step 2 is to find the molar mass for each compound. So I've already done that for you. This is just adding up the masses from the periodic table. I think I rounded a little bit on these, so my numbers might be slightly off. So ammonium nitrate's 80 grams per mole. Ammonium phosphate's 149 grams per mole. The next step is to find the percent by mass. To do that, you just do part over whole times 100. So my part would be however much nitrogen weighs in each of these compounds. My whole is the entire molar mass. And then I'm going to multiply that by 100. So let's just see what that looks like. Okay, so my total mass of nitrogen and then my total mass of ammonium nitrate. So my mass of nitrogen in this compound is 28 because I have 2 nitrogens. I'm going to divide that by 80, which is my mass of the whole thing, and then I'm going to multiply by 100. And that'll give me about 35%. So that means 35% of ammonium nitrate is nitrogen. I'm going to do the same thing with ammonium phosphate. I have 42 is my mass of nitrogen because I have 3 nitrogen. And then I'm dividing that by 149, multiplying by 100, and I get 28%. So ammonium nitrate would have the most nitrogen in it. It would have the greater percentage. Let me scroll through these. The most important application of the mole, outside of measuring chemical reactions, is determining the empirical formula and the molecular formula for a compound. The empirical formula just gives us the simplest whole number ratio of atoms. The molecular formula indicates the exact number of atoms in a molecule. This is what we usually see as the molecular formula. If we isolate a compound from nature, such as a cancer-fighting substance from a plant, it's important to know its empirical or its molecular formula so that we can synthesize it and make it in a lab. Aspirin, which is one of the world's most widely used pain relievers, was originally isolated from the willow tree. So here's how you write the empirical formula. These steps are listed for you, and we're going to walk through them right now. Excuse me. Okay, here's my example. Sulfadiazine, a sulfur drug used in the treatment of bacterial infections, is found on analysis. It has 48% carbon, 4% hydrogen, 22.4% nitrogen, 12.8% sulfur, and 12.8% oxygen. The molecular mass was found to be 250 AMU. Calculate the molecular formula for this drug. So first we need to find the empirical formula, and then we can go back and find the molecular formula. We're going to assume that we have 100 grams of this substance. So now all I have to do is change my percent to grams. So here's what that's going to look like. Since we're saying that we have 100 grams of the substance, it's very easy to change percent into grams. Next step is to convert my grams to moles. So I'm doing this for every single element. I can do 48 grams of carbon divided by its mass, and that gives me 3.9964 moles of carbon. I'll do the same thing with hydrogen. I'm dividing. And I'm going to do that with all of my other elements. So now I have moles of nitrogen, I have moles of sulfur, and again, all I'm doing is dividing my grams by its molar mass to get moles. And finally, I have oxygen. My 12.8 grams divided by the mass is 0.8 moles of oxygen. So now that we have everything converted into moles, let's look at our next step. Step 3, divide by the smallest number. Our smallest number is 0.399, so all of our answers that we got in moles, we're going to divide by 0.399. So here's what that looks like. Okay, so these numbers that are highlighted in blue, those are going to give me my numbers for my empirical formula, but I'm going to round them to the nearest whole number to plug them into my empirical formula. So here's those numbers again. They're going to be perfect whole numbers. So when I plug that into my formula, I have about 10 carbon, 10 hydrogen, 4 nitrogen, 1 sulfur, and 2 oxygen. So that yellow formula is my empirical formula. That's the smallest number I can have. Now we need to determine the molecular formula by using that empirical formula. So we know the molar mass given in the question is 250 atomic mass units. Our empirical formula is listed right there in yellow. If we add up the molar mass of this formula, my C10, H10, N4, S1O2, we would get 250 AMU. So that's the same mass that they gave us in the question. So our molecular formula will be the exact same. Sometimes it will change. The molecular formula will not always be the same as the empirical formula, okay? If the molecular mass had been 500 AMU, then we know, like if that's what we found, then we would know that the real formula would be twice that of the empirical formula. So if that was the case, if it was 500 AMU instead of 250, then we could have just doubled all of our numbers in the empirical formula, and it would be what's highlighted there in yellow. A couple other things, these are just helpful clues and hints. If one of the values contains 0.333 or 1/3 and the other values are whole numbers, you can just multiply everything by 3 and that'll give you some whole numbers to work with. Same thing if it's 0.67 or 2/3, multiply everything by 3 and it'll even out. So right here in my example, I have CHO. My C is 2.67. I can multiply everything by 3 so that I can get whole numbers. That will be easier for my empirical formula. If one of the values is 0.25 or 1/4 and the other values are whole numbers, then just multiply everything by 4. So in my example, I have 2.25 carbon. If I multiply that by 4, that gives me a whole number, which is 9. You can only do that for the empirical formula. Okay, so that's all for this section. I'm going to add another video for stoichiometry part 3. We are doing parts 2 and 3 on the same day in class.